So now we know a lot about Newton's laws of motion, mostly the second law, and we know a little bit about free body diagrams. So we're going to be looking at specific case examples that will just help us get into the mindset of using Newton's second law and see it with a bunch of scenarios. So we're going to start with the first one. Okay, so here's our first case. Case 1, normal force on a level surface. And here I have the picture of what I'm exactly talking about. So we're going to be looking at this and doing Newton's second law. So what I notice here is that there's a gravity force, gravitational force. It happens right here at the center of gravity, or the center of mass if you want to think of it like that. And it points down. And that's the weight of the object, right? And then now we want to look at the one that is perpendicular to the surface, called the normal force. And we'll see that the normal force will become kind of like a theme in this video, since we're looking at normal examples. So the normal force actually pushes up from the ground, like here, right where the block is, and it pushes up, right? That's where it's located. If you're wondering, it always happens at the point of contact. It's kind of like a contact force, while the gravitational force is more like a long-range force. Maybe you've heard of that before. So then we want to use Newton's second law. We are focused only on the y component here, right? Because it's vertical and it's not moving, so we can safely say it's 0, right? There's no acceleration at all. Alright, so now let's sum the forces. So I'm going to define upwards as positive just to help me. The normal force minus the weight is equal to 0, right? That's the net force, because this is a positive force and this is a negative force by this convention. In other words, I'm going to write our final result here in blue. In other words, the normal force is equal to its weight on a level surface, right? So as you see, this is like the basic example. This is a very simple one that we just find the normal force. So let's move on to the next one. Alright, here's our second case. Normal force on a level surface with an applied force. As you can see, right here is the applied force, and it's pointing downwards, right? So we just want to get used to this. I already drew the weight and the normal force, and we're just going to work with this applied force as well. So the main problem here is that we want to break it down, every force, into vertical and horizontal components, right? And this is not in vertical and horizontal. So I'm going to just give this name F, right? FA for F applied, right? I want to specifically break this type of vector down into components and then draw a free body diagram from that. Which is not too bad, because remember, we can easily break a vector into its components using this angle, right? Remember that the adjacent is the cosine of that, FA cosine. And then the opposite of this angle is the sine, FA sine. Right? So here, let me put arrows on top. So now we can kind of draw a better free body diagram with components on it. So we have the weight, mg. We have the normal force, normal. I'm going to write it with capital N. Let me write this lower. We have another thing pointing down, which will be our FA sine theta. And then we have something pointing this way, which is our FA cosine theta. So now we want to use Newton's second law. And we have to describe it in two equations. One is up and down, and one is left and right, right? Okay, so let's go ahead and try that. So we have the one in the x direction is probably the easiest one. It is accelerating because there's only one force being applied to it, and there's nothing that balances that out. So let's see. If I were to describe the convention to be this way, I have to take a little cut here because I think my OneNote crashed, so I have to reopen it. So back where we were supposed to look at the x direction, or the horizontal components of the Newton's second law. And I'm going to define upwards and rightwards as our positive directions. So this is not too bad, right? The only force here is just the FA cosine theta. Oop, this thing I noticed also disappeared when my OneNote crashed. And it's equal to MA. So that is our kind of, if you want to think about it, our horizontal result. And then we can solve for whatever. But we're actually also have to look at the y component, which is kind of more involved in this problem. It is not moving, I'll say, so it is not moving vertically, so it has no net, the net force is 0. So remember, upwards is positive and downwards is negative, so it is basically the normal force minus its weight minus the applied force in that direction. And I'll solve for the normal force here. So it's just equal to the sum of the applied force and the weight. So this is, let me write that in purple actually. So just so you know, we reached the end of our, I guess this is kind of like, all these problems are kind of like derivations from a diagram, if you want to think of that. So this is our second case where we have this. The next case we're looking at is a normal force on the level surface under acceleration. So that's a lot to handle in just one kind of description. But basically what it is, it's, let's say you're on an elevator that's accelerating upwards, right? With an acceleration pointing upwards. We want to find that normal force. And that shouldn't be too bad, because we're just going to use Newton's second law in the y direction. And it's accelerating, so it's ma, right? So then we just sum the forces. I'm going to define upwards as positive. And so we get the normal force minus the mg is equal to ma, right? And these should all have vectors on it. Sometimes I might forget to draw vectors, but we know what they indicate direction. So I'm going to solve for the normal force like always and see what we get. Normal force is equal to the weight plus the acceleration times mass, right? But I guess I'll make it more pretty actually. So the normal force is equal to the mass times the sum of this, right? These two quantities. So as you can see, Newton's law is kind of, you get the same idea, right? You want to draw the forces, upwards and rightwards is usually positive, and then downwards and leftwards is negative, and then you draw, if you have a horizontal component, you'll have to have two equations. If it's just a vertical, you'll have one. So let's do one more, and this is the hardest example I'll give for normal force. And our last example, we have normal force on an inclined plane, and this is probably one of the most classic examples in physics, the inclined plane problem. So here we have it. This one's kind of weird because the normal force is kind of pointing diagonally, right? It's normal to this incline, right? That's why we call it normal force in the first place anyways, right? That might be, people sometimes don't recognize that that's what the normal force does. It's just a force that points normal to the surface, or if you don't know what normal means, it says perpendicular to the surface, right? Normally we would have to break all this to components, but actually let's think about this, because I kind of want the normal force just to be normal, just that in itself, not in its components. So what we do is we picture this and we pretend we kind of rotate it so that the axes look something like this, right? Where this is the positive, I'll define this way, and downwards as a positive. So we kind of want to break it down into parallel and perpendicular forces, if you want to think of it like that. So let's think about that. So we have this. Our perpendicular force is the normal force. So let me draw that in green. Like that, right? This is our normal force. And then our weight, if we were to tilt it a little, it would kind of stick out this way, mg. And let's do like a quick side work really quickly, because I want to show you something. If we were looking at more of that, so here's the g, and here's like the surface, not the surface. Let's do it like this. Let me just draw it. Here's that force, and here's the angle, and we kind of want this. What I'm gonna try to show you is that this angle here is actually here, the same as this angle. And the way I'll show you that is, let me just extend this and drop it down. It's kind of like a geometric proof, so that's kind of fun, I guess. So we know that this angle is 90, right? So then this angle here should be the sum of this triangle that it's trying to make is 180 minus 90 minus theta, right? Or 90 minus theta. And then I'm going to make the statement that this here, this angle, is a right angle. So what I'm trying to say is that 90 plus these plus the what we're given, right? The one I just found, 90 minus theta, plus that angle is equal to 90 degrees, and that's true, right? So we know that these two must be they must be the same angle. So I'm going to erase this really quickly. Just think of it like that. We're going to look at that. So this is that angle right here. So in other words, we want to break it in such a way that this can be broken down. If this is the hypotenuse, then it should be like this, like that. So let's see, what is the adjacent part? This is the mg cosine, right? This is the adjacent to the angle, and this is the mg sine. So now we can use Newton's second law, but instead of using x's and y, I'm going to use a parallel, and I'm going to use a perpendicular, right? The net force is the parallel stuff, so anything going along this way looks like it's going to accelerate this way, right? If it's no friction, and the only force is the mg sine theta. And I define downwards the slope as positive, right? This way. And this is equal to ma. I guess if you want to be simplifying, you can do it like this. You just maybe want to solve for acceleration, and we found that. So let me just write the final statement here. A equals g sine theta. Now we want to look at the perpendicular part, right? So the perpendicular part is not moving if you think of it as perpendicular, right? Anything perpendicular, it's not going to suddenly jump out of the plane or go into the plane anymore. It's going to be it's going to stay like this, stay on this kind of axis. So that's why there's no acceleration. And now we have to sum all the forces, right? Normal force minus the mg cosine theta is equal to 0. So that means we get our final result already just by adding mg cosine to both sides. So mg cosine theta. And these are our final results. So let's look back and look at a quick review really quickly. So we looked at a very easy case where we had normal and a weight. This is the process how we do it. And then we looked at something where we applied a force and an angle, and then just involved breaking the force into components and adding it to our free body diagram like this. And then we have to use two forms of Newton's second law, right? One in the x, one in the y. This one was just an example with acceleration, right? Vertical acceleration, so it wasn't too bad, right? Because we just have to account that this is not 0 anymore, it's ma. And then the classic example, the inclined plane, we just have to tilt the axis in a way such that it's a parallel direction and a perpendicular direction, because it's so much easier to write this in terms of itself and then the weight in terms of the angle right here. And I showed you why that angle is this angle right here, and then we just use Newton's second law to get our answer. So these are 4 cases dealing with normal. So next time we'll look at some different cases for different forces.